Welcome back to the second lecture of week 11. In this lecture, we will discuss the mean value theorem and some of their basic applications. The first theorem that we will examine is the standard mean value theorem that you should be familiar with from your calculus course. The second, Cauchy's mean value theorem, is something not always taught in Calc 1 classrooms. While the proof of Cauchy's mean value theorem is largely the same as the standard one, with some minor modifications, its geometric meaning is a bit harder to grasp, unlike the standard mean value theorem. In a course in analysis, the main use of the mean value theorem is for transferring information concerning derivatives to information about the function itself. Another way to think about it is, seeing that a derivative describes instantaneous behavior or infinitesimal properties, the mean value theorem is a way to transfer information from the instantaneous to the sustained, or from the infinitesimal to the tangible. We will see some basic application of this in this lecture, as well as a more advanced application in lecture 4 of this week. The material covered in this lecture can be found in two separate spots in your textbook. Most of what we will discuss are on pages 233 through 235. The exception is Cauchy's mean value theorem, which is found on page 241. Let's get started. The first theorem we will prove today is the classic mean value theorem. It is a generalization of Rolle's theorem from the previous lecture. Recall that Rolle's theorem states that if a function is differentiable and its global trend is stationary, reflected in the fact that the function outputs f of a and f of b are the same, then the stationarity is reflected in the derivatives, in that we can find the point between a and b where the derivative vanishes. The mean value theorem removes the assumption that the global trend is stationary. Instead, it asserts that the rate of change as exhibited by the global trend, meaning the slope of the line connecting f of a to f of b, is reflected in the derivatives. So, the basic hypotheses are the same as Rolle's theorem. We take f to be defined and continuous on a closed interval ab, and we assume f is differentiable in the open interior of the interval. Then we can conclude that there is some c strictly between a and b, such that the derivative f prime at c equals to the rise over run from a to b, namely the quantity f of b minus f of a divided by b minus a. You have certainly seen this theorem before in your calculus course, so I will not belabor the geometric meaning. The proof of this theorem is fairly simple. And this illustrates one of the tricks in the presentation and development of mathematics. Mathematicians like to, whenever possible, divide up proofs into manageable chunks, and in presenting them, we like to not shoot for the moon in the first go, but build up our machinery in steps. This also means we often end up in situations where the proof of a theorem is by providing a transformation of the inputs in such a way that a previously proven theorem can then be applied. This is a general proof technique of reduction to known cases, or what I like to call passing the buck. What we want to do here is to make use of Rolle's theorem. Now, Rolle's theorem only works for functions whose outputs at a and b are equal. Our function does not satisfy this property, so first we create the function L of x given by f of a plus m times x minus a. The slope m is the rise over run of the function f from a to b, namely the value of f of b minus f of a divided by b minus a. The key thing to notice about L is that it is a continuous and differentiable function, and we know that at every point its derivative is exactly m. Since the function L passes through f of a when x equals a, and has its slope the rise over run of f from a to b, we also know that L of b is exactly equal to f of b. So, if we set the function g to be the difference between f and L, we will find that g of a and g of b both vanishes. And since f and L are both continuous on the closed interval AB and differentiable on the open interval AB, so is the function g. This means that g satisfies the assumptions of Rolle's theorem. And applying it, we find that there is some c in the open interval AB such that g prime of c is 0. But g prime of c is the derivative of f minus the derivative of L at c. The latter we know is exactly m. So we have that the derivative of f of c turns out to be exactly the rise over run of the function f over the interval AB. And this proves the theorem. In this proof, in order to make use of Rolle's theorem, we had to modify the input function f to get a function g such that g of a equals g of b. To do so, we subtracted the linear function that goes from f of a to f of b. What if instead of a linear function, we just subtracted some other random function that shares a value with f at both a and b? You will be asked to explore that on the exercise sheet. The next theorem we will prove is a further generalization of the mean value theorem due to Cauchy, and so it's usually called Cauchy's MVT. We will discuss its meaning after we give the proof. For now, let's examine the statement. The statement now makes exactly the same assumptions as we did for the mean value theorem, except we are asserting that the hypotheses hold for two functions, f and g, simultaneously. The conclusion says that we can find a point C in the open interval AB such that the slope of f at C times the overall change of g is equal to the slope at g at C times the overall change of f. We see that if we plug in g of x equals x, the identity function, then Cauchy's mean value theorem actually contains the standard mean value theorem as a special case, since now g prime would equal 1 and g of b minus g of a equals b minus a. The proof is in very much the same spirit as the standard mean value theorem. Again, we wish to use Rolle's theorem. Again, we are not given functions whose outputs at a and b are related. So we have to start from what we are given and make a function that has output b equal to output a. The trick we will be using is the function h given here. We set h of x to be equal to f of x times the overall change in g minus g of x times the overall change in f. Notice that the overall changes in g and f just give constants independent of the input x. If we do a little bit of algebra and compute exactly the values of h of a and h of b, after expanding out the four terms that show up, we see a miracle occurs. First, for each of h of a and h of b, out of the four terms in the expansion, two of the terms cancel, so only two are left. And the two remaining terms for h of a turns out to be exactly the same as the two remaining terms of h of b. I'll pause a moment here for you to mentally verify the computation and check that indeed h of a equals h of b. Now, since h of x is given by the difference of two functions, each being a constant multiple of a function that satisfies the continuity and differentiability assumptions of Rolle's theorem, this means h of x now satisfies all of the conditions for Rolle's theorem to apply. And therefore, from Rolle's theorem, we conclude that h prime of c equals to 0 for some c. Plugging this back into the formula for h, since h prime is equal to f prime times the total change in g minus g prime times the total change in f, we see that H prime C being 0 is exactly what we set out to prove. Now, if you are amazed at how we chose H so that this works, don't be. The process of discovery in mathematics is not one where a random idea pops into your head and then you set out trying to prove that idea is true. There is not a mathematics god setting a divine problem set for you to solve. More likely what happened was that Cauchy asked himself, hey, looking at Rolle's theorem, it looks like when given two functions f of g, it looks like I can build this function h that satisfies the hypothesis of Rolle's. Now let's see what happens when I apply Rolle's theorem to it. Oh, that's neat. Let me write it down as a theorem. A lot of the discovery of new mathematics is just like the creation of new recipes in cooking. You take known ingredients and combine them in new ways. Sometimes you get a dish that tastes disgusting, those you stick into your drawer and try to forget about. Sometimes you get a dish that is exciting, those you write up and publish. And you write them up by stating the theorem first and the proof second, so people can marvel at the ingenious way you put together your ingredients to make the proof work. When in fact, it is that you started by just throwing random ingredients together and this theorem happened to work out well. But they don't need to know that, do they? Anyway, back to the theorem. Let's talk briefly about what Cauchy's theorem means. Geometrically, this theorem is what happens to the mean value theorem if instead of thinking of the graph of a single variable function, you think of the graph as being described by a parametric curve. You may remember from Calc 2 that there were two different ways of computing arc length of a curve. There's one way when the curve is specified as the graph of a function, and a different way when the curve is specified as the graph of a parametrized curve. This is sort of the same idea. First, let's rewrite the conclusion a bit. Suppose that neither g prime of c and the total change in g is 0. We can divide through and rewrite the conclusion of Cauchy's theorem as the ratio of derivatives of f and g is equal to the ratio of their total changes. This makes it easier to connect with the parametrized curves picture. Consider now the parametric curve where the y-coordinate is specified by the function f, and the x-coordinate is by the function g. Then, you may remember from Calc 2 that the slope of this curve at time c is exactly the ratio of the derivatives f prime over g prime. If g prime is 0 and f prime non-zero, this means the curve has a vertical tangent line. And the overall rise over run of the curve over the time period from A to B is the change in y values over the change in x values, which, since the y is specified by f and the x is specified by g, is the total change in f divided by the total change in g. And so, we see that if we interpret Cauchy's mean value theorem using parametric curves, it is again saying the same geometric statement as the standard mean value theorem, namely that the total rise over the total run of a curve is represented by the slope of the curve at an intermediate point. We prefer in this case to write the final conclusion in the product form rather than in the quotient form, because this way we can handle what happens when we have infinite slopes, or when the total change in x is 0. This is similar to how the parametric curves allow you to describe more curves using equations compared to the graph of a single function. For example, parametric curves need not obey the vertical line test. It turns out, however, Cauchy's mean value theorem can also be used in situations that are not geometric, and in those cases it gives an upgrade to the standard mean value theorem. We will see this in the final lecture of this course. With the two main theorems out of the way, let's talk a little bit about some basic applications. First, a corollary. This says that if f is a function defined on an open interval that is differentiable at every point with derivative 0 everywhere, then f is constant. Very importantly, we can arrive at this conclusion without using any facts about integration or the fundamental theorem of calculus. This is a statement that makes sense entirely just using the derivative concept. Let's prove it. We will prove by contradiction. Suppose for contradiction that f is not constant. Then there are some points c and d within the open interval ab such that f of c and f of d are not equal. This being what it means for a function to be not constant. Now, as we proved last week, a function differentiable at a point must be continuous at that point, so the fact that f is differentiable at every point inside the interval ab means that f is continuous on the interval. And in particular, it is continuous on the closed interval CD. So, we can apply the standard mean value theorem to it. This tells us that there is some gamma between C and D such that the derivative of f at gamma is the change in f over the interval CD divided by the width. Since f of D and f of C are not equal, the numerator is non-zero, and so f prime gamma is not zero. But this is a contradiction since we assumed as part of the hypothesis that f prime is equal for every point in the interval AB to 0. So this corollary is what I meant by when at the beginning of this lecture I said that the mean value theorem transfers information from derivative to the function. In this corollary, we assume information about the derivative, that it is 0 everywhere, and this gives us information about the function, that it is constant. The way this works is via the contrapositive of the mean value theorem, which, if we think about it, says that if the slope of a function is never a particular number, then the function cannot have any interval on which the total rise over total run evaluates to that number. And here, since the slope is never any non-zero number, the total rise of the function over any interval cannot be any non-zero number, and hence it is constant. We see this principle at work again in the next corollary. In this corollary, we will show that if f is differentiable on every point inside an open interval AB and f prime is strictly positive, then the function f is strictly increasing on the interval AB. So thinking about what we just summarized, in order to transfer our information about the derivative to the function itself, we should aim to use the mean value theorem in reverse and think about what f prime are forbidden by our hypothesis. In the statement here, we assume that f prime is strictly positive, and so the information given to us is the same as saying that f prime is not allowed to be negative or 0. And so the mean value theorem would say that over any subinterval, the total rise is then not allowed to be 0 or negative, which is the same as saying that the function is strictly increasing. We will write out the full proof in a moment. Prior to that, however, let me give one remark. This corollary also holds with different versions. If we assume f prime is always non-negative, then this will tell us that f is increasing but not necessarily strictly so. If we assume f prime is always strictly negative, then this will tell us that f is strictly decreasing. And if we assume f prime is always non-positive, then this will say that f is decreasing but not necessarily strictly so. The proof all work in more or less the same way. Now let's give the proof of the version we stated, with strictly positive f prime. Again, we will argue by contradiction. Suppose f is not strictly increasing. This would mean that there are some points c and d in the domain with c less than d, such that f of c is at least as large as f of d. Again, we know that differentiability implies continuity, and so we satisfy all the hypotheses of the mean value theorem. This would mean that there is some gamma between CD, where the derivative is equal to the total rise over total run. But now since f of c is at least f of d, the numerator must be non-positive, and the denominator, however, is positive since d is greater than c. And so the quotient is non-positive. This then contradicts our assumption that f prime is always positive. Okay, that's it for this lecture. See you next time.